Welcome to this session for advanced combinatorics in Wolfram language. So I'm Shenghui Yang. I work for Wolfram Research as a developer. For the topics I covered in past years, mostly for competitive problem solving, and usually include geometry, number theory, and combinatorics. So this year, I would like to focus on combinatoric part for Wolfram to solve those advanced combinatoric problems only using Wolfram language. So for this topic, so we not only just focus on the problems and typically the theorems I picked up, and typically I want to mention that after years of development on the building functions and also for the functions with a community-driven repository, the Wolfram Function Repository, we have accumulated a decent amount of good functions that can be used for combinatorics analysis. In this talk, I would like to just demonstrate how to use some of the functions, and also bring the awareness that there are such functions existent in the function repository, so that you can either as a hobbyist, or if you are advanced mathematicians, you can take advantage of the curated functions to help your own research. So here I have a nice diagram that I used as a sort of like Christmas tree for the cover page. So I'm going to show how you program that and use a similar function already inside Wolfram Function Repository to build such a nice diagram. So the first function that I would like to talk about is about ordered within and ordered between partitions. So this is related to a function or a number, just like factorial number or Stirling numbers. It's called a Lach number. This describes how many ways that you can divide a set of undistinct elements into k non-empty blocks. So there's a very nice Wikipedia page about it. Let's take a quick look about it. So say if you have like 3 elements in the set, so you can break it down into either entire thing as a one partition, or you can make it into 2 partitions or 3 partitions, like 1 is itself, 2 itself, and 3 itself. So in this type of partition, what's important is the orders inside these tuples. So that's why I called it ordered within, but unordered between partitions. So in this case, 1, 3, 2. If you take 3, 2 as a whole partition, and you swap the 3, 2, and 1, or 2, 1, 3, or 1, 3, 2. So this partition, the order between the partitions are irrelevant. So for this type of partition, there's this Lach number describes the exact enumeration for such occurrences. So there's a function already curated inside Wolfram language, the function repository. So you can just you type resource function Lach L, and you see there's a small tooltip pops up just right below the functions. So if you click the book sign here, so it automatically brings you to this function repository page, and you can learn about the details of the functions. And if you want to learn how the function is created, you can just click the source notebook, and you can download this source code behind it. And also what you can do is you hover this mouse over there, and you click the notebook sign. So it will automatically brings the domestic notebook for you to show how this function is defined. So this function, it's really straightforward to use. For example, here I have 8 elements. and I want to take a look at how many ways I can partition into one piece, 2 pieces, 3 pieces, and 4 pieces. So you can just run it, and it will show you these numbers exact about the Lach enumeration described in this table. So you can see this number here, right? And you can also create a similar number, a similar format of a number inside your own notebook. So this is a function that I think is extremely useful to create such a two-dimensional Lach plot. So a Lach number grid. So you can just create using tabular. So one thing is extremely useful for tabular is the format or the color of the elements automatically switch between the dark mode and the light mode of the notebook. So you don't have to worry about the background, and it automatically handles the colors very well, and the numbers are formatted nicely. So the only thing that you want to be careful about doing that is you can see that I use a function called the pad right, because for one, you start Lach number 1 for if the second argument is larger than 1, because you say you only have one element, so there's no way you can break it down to like 2 parts. So it automatically does not evaluate. So you have to put a pad right, so put all the zeros inside the list. So in this way, this function will become sort of a rectangular array. So you can just pass this value directly into this tabular. So if you use this tabular pad right and then apply on the table functions, so this one basically generate a triangular shape for you. And then this pad right is add the zeros to the right hand side of your list. And because I'm only interested in 12 terms, so pad right, the syntax is pad the list up to 12 elements. So if I only have 1 in the beginning, so I automatically have 11 zeros after that. And if I have 2 elements, then I have like 10 zeros behind it. So the same thing applies to everything until the last item. The last item, because it already has like 12 elements. So pad right 0 does nothing to that. So you have a like very nice grid of numbers that you can observe or do some enumeration or OEIS search by yourself. They should look exactly like this table. So I think a tabular is quite a nice addition for such function. And if you want to learn how this Lach number is defined, it's actually quite straightforward. So because if we have k partition, but the order of the k partitions are irrelevant, so definitely I will have something like k something divided k factorial. But all the numbers inside can be arbitrary order. So there's generated, of course, by n factorials. And then you can see that clearly this part, the binomial n-1, k-1 part is quite familiar to people are familiar with the combinatorics, because this is exactly the formula inside the standard star and bars construction. So you can think about it. This is a partition as you plug bars into between the elements. So that's why you have n-1. If you have n elements, then you have n-1 gaps, and you can plug in k-1 bars inside it. So this part gives you exactly the matching argument inside the stars and the bars combinatorics Wikipedia page. So this is a quite a straightforward way to construct the Lach number from this definition. And also we can just if you instead, this is kind of my generic workflow. So if instead of Lach number, already you have the formula for that. But if you happen to encounter this type of numbers inside your notebook, of course, you can open a browser and search for OEIS for this number, but also this very handy function inside function repository. You do the same thing. You hover your mouse over there and click the left-hand side of the tooltip. So usually you only need to read these documented pages for yourself, and instead of just reading the source notebook. So most of example page for the BF function actually looks very similar to the built-in functions. So you can just, okay, let's just use the simplest argument. So it looks like I just type a function and plug a list of numbers inside. So this is exactly what we do here. So you call this function, and this function will give you all the entries in OEIS that contains this guy. So even though I have like different variations, but for most time it just looks like it includes the keyword lach, right? Triangles by row. So this is also like look like a lach function, but with n-1 and k-1, like a bit shift, kind of shifted to the left of this guy. And also this is an unsigned lach number, and this is probably some something also related to lach, but it's expressed as some sort of like generating functions or the coefficient in other algebraic structures. So it's related to Laguerre polynomials or something. So this is give you sort of very smooth workflow. So if you just want to do this type of calculation and it stays inside the notebook. And this function gives you a little bit more. It's called OEIS sequence data. You can also hover the mouse over there and click this guy, and you can bring up this function. It also shows what kind of argument, second argument that you can put inside this function. So you can of course put something like links. So it will show you the hyperlinks that you can jump to the OEIS page. So for me, I just put a dataset function, argument here. So if I run it, so it returns quite a detailed, data set that includes a lot of useful information for me. And notice the first argument here, instead of this number, I just copy the OEIS ID here, and this function just grab everything from the web page and download it for me. So you can see there Wolfram Language code, and this basically, if someone contributed code online, you can just copy this part and click that. I mean, you can see that the code is here. And if you want to see the definition, you can name. You can just click name, and it shows you the string of name. So because this returns a canonical dataset object, so everything like the functions in dataset will work automatically. So you can just grab the content inside and do more research by yourself. Okay, and so in the last step, we showed how you do the enumeration. So just count the number of that. But sometimes you want to generate this so random entity by yourself. Okay, so a better way is to generate the worst way is to generate n-factorials everything and delete something, right? So this usually doesn't work because like lach number, it's n-factorial times a binomial, so it increases very quickly. So you do want to follow the like a sort of smarter way to generate only one example or one entry, but follows exactly the correct probability. So this is something I feel like it's extremely important in this type of combinatorics analysis or research, because this one will give you very feasible way to generate random permutation or random partition with some certain constraints. So in this code, I will generate the example with the correct probability, follows the correct probability. But I do have some mark around the correct, because there are different way to say how correct this is. For example, this is a sort of a more like naive way comparing to the other way I'm going to quickly mention about that. So let's first take a look at this example. So I have 8 elements, and I want to generate the example with like 4 partitions. So first I just assign n equal to 8 and k to 4, and then I just generate a random permutation. This is a sort of a random permutation of all elements, and then I treat the elements and stars and insert the bars between them. So this is exactly what we do, follows the formula. So what this says, I insert a bar at the second place, and insert a bar at the third place, and insert a bar at the 6th place, because I want 4 partitions. So the most of bars I can insert is 3. So and then I can just actually insert the bars between the elements. So the 2 here, the second position is you can treat this comma as a new list of elements. So 2 means I replace the second guy here with a bar, and I will replace the third one as a bar. So if I have 2, 3, that means this guy is a partition with only 1 element. And then if I have the indices here, what I need to do is convert it into a list of lists, because eventually, if you do partition, you can think about it. You take something from the list. So for 1, 2 is like if I have replaced this guy as a vertical bar, so I pick up 1, 2, and then the 3, 2, 3, because this is sort of like between the second bar, third bar. So the index for the element itself is 3, and I only take 3. So it's a 3, 3. So I use a duplicated, because that would be really easy for you to apply the take function to grab them. And then this is sort of the correct way to convert bars into the indices of the elements in the list, and do take, which is same as the partition in the definition. And then because this type of a thing follows definition that the orders between the partition really doesn't matter. So what you can do is you do a lexicographic sort. So the way to say the order doesn't matter is equivalent to say there's only 1 order. So the only 1 order, I can always choose lexicographic sort. So this actually will generate the Lach partition about the correct sort of the correct probability for all the space, for everything in the sample space. So because this is a sort of like saying, I partition all the unfactorial stuff, and then find the right and then reorder everything according to this way. There's another way to do that is if you only sample those things look like this inside the entire, so make the like say 4 partitions as partitions of all the 4 elements. So it actually will change the weight of the occurrence of this type of occurrence. For this way, the occurrence of this type of partition actually will change its weight because of the definition of the Lag partition inside the entire example space. So the second one would be kind of, I think it would be more useful, but I did not cover that in this topic here, but I would like to contribute to a community post for that application. And then the other so for those combinatoric stuff, usually you have more than one way to define it. And this function is actually borrowed directly from the Eulerian number triangle WFR functions. And then I simply modify the functions. So what you can do is using the definition of the recurrence of Lag. So it looks like very much look like a binomial sequence. So the sort of the value equal to the sum of the value from its two shoulders. So if you are familiar with Pascal triangle, this is exactly how the number like in the next layer was constructed. And in this case, we have sort of a customized weight for that. So instead of just doing the sum of the two things. So to create such a Pascal triangle diagram, I want to include the weight inside it. So what I can do here is I put a weight and then this function. So this is a very nice like Pascal-like triangle, and you can have all the numbers. And if the number is more than 4 digits, I make a tooltip so you can have everything inside a well-organized tree and numbers. If you want to know the numbers, just hover a mouse over there. This shows it nicely. And you can see that this number should be the sum of these two numbers, but not directly, but you have to add the weight to that. So this number is 1 times this guy plus 11 times this guy. You can check all the numbers here. And this number, this function will enumerate everything for Lag number correctly in the tree. Okay. The next function that I have added into WFR a while ago, it's called the Foata transform. So this is something like related to sort of a bijection proof between Eulerian number and Eulerian numbers and the number of accidents in the combinatorics. So there's a web page for that. So basically, I converted the algorithm on this web page, so you can read it. The key example steps here is you do partition, sort of a cycle partition for this like permutation. So you have original number is always 1, 2, 3, 4, 5, 6, and 1 to n, and then you permute it. And in Wolfram language, you use a function called find permutation. So it will generate these permutation cycle for you, and then you rotate those cycles. You don't permute the cycles arbitrarily. You rotate the numbers inside it. So you keep it like same cyclic permutation in each cycle, so that the first element is always the largest. And then you sort all the tuples, just like we did in Lag number, sorted based on the first argument. So if you want to see how it works, you can just use these functions inside Wolfram Language Function Repository. You can see their Foata transform. You can just hover that and click help, and it brings you to the function page for this permutation. So the permutation shows that if there's a permutation here, it says the descent. There is some definitions you need to take a quick look at. As a descent, if the pi I is larger than pi I plus 1. So say you have this permutation here, right? If pi I is greater than pi s 1, so absolutely 8 is more than 6. So this gives you account for descent. So ascent is something like different. You have basically swapped the comparison. Excedence is the value is greater than the indices itself. So you say 9 is included for excedence because 9 is larger than 4. So McMahon, I think there's a mathematician discovered the correspondence a while ago. So she showed that the number of permutations with a given number of descents is a kind of same thing as the permutations with a given number of excedents. But the construction proof is quite late. It's very close to 1970. So this guy, I think it's called, his name is Dominic Foata, showed that there are a couple of different permutations that you can do. So it's called a Foata transform. So this way is exactly described inside this web page. So if you want to know how this function is implemented, click the source notebook and you can take a look at it. And these are basically the examples that I have curated inside this is exactly the same thing covered in the documentation for the WF function. So you can just play around it or just go to the page for the Foata transform, and you can see there's properties and the neat examples. So you can play around the examples here. And also there is an inverse Foata transformation that converts the a permutation with a given excedence back into the permutation with the correct number of descents. So in this case, you can just using the same resource functions, there is an inverse Foata transform. So you click help, and it shows you the definition of the functions and how it's described in history. And the neat example shows you the correspondence. If you have two random permutations, they have the same number of excedents and descents, so they should look like this. Basically, this is how they are related. Okay, and the last one I want to quickly mention is the new tree functions introduced after version 13, I think. This tree function is really useful. You can use it for very many different kind of tree permutation or recursive algorithm that you can work on trees. So this is actually quite interesting algorithm. It took me a while to understand how it works. So you can read it by yourself, and interestingly, we also have this guy inside the function repository, and I added a while ago for this function. It took me like a while to understand how the algorithm works. So before you jump into the functions, I highly recommend you to watch this YouTube video on about this collagen Palazzota tree. So it actually gives you some examples, show you how this recursion works inside this function, inside this recursive formula. So this L and R are sort of statistics about the subtree of this particular function. So you can just go to the function page, click source notebook to find out how it's implemented, and we have some nice examples under it. And this function, this page, this scope part is really important because it faithfully replicates slides inside the YouTube video that I linked. So once I created this part, I finally understand how the tree is constructed according to the algorithm discussed over there. And I think that's everything that I want to talk about. Oh, and the last one is the uniformly random full binary tree with the labeled leaves. This function is also available inside the function repository. So this is something like that it's really interesting. So if you want to generate like random binary trees, you really have to understand how the recursion formula for Catalan number is calculated. So if you do that just by random permute or something, you will have like really biased result. It only works if you follow the exact Catalan number, how the Catalan number is calculated using the recursions. So what you can do is I can show you quickly how this guy is related to that. So this is a tree. How it's related to Catalan number is not really obvious, but if you convert it into one of the definition for Catalan number is you count the enumerate of the permutation of the matching parentheses. So it's called a big word, and you can just take a look at the result. It is true because you can see that the parentheses are always matched. So there's a for everything like for let's say you go from the first one to the 10th one, or the first one go to the 11, 12, or anything like that. So you will not have a more right parenthesis than the left parenthesis. So this is in this way, this parenthesis is always matched. So you won't have something like unmatched parenthesis. So this is exactly one of the equivalent definition for Catalan number. So if you enumerate, tree this way, the probability of generating such configuration is described in Catalan number. So okay, so this is the end of the talk. I actually use the most examples from the existing WFR repositories, and you can either use the function defined in this notebook, or just directly jump to the functions inside the WFR and read the source code, or using the documentation page. So it is really good collections of this type of advanced combinatoric stuff. You can play around with the list or numbers or trees. So feel free to play around and let me know if you have some questions. I can answer you. No, it's not. It's not inverting permutation. It must be doing some of the rotations of these guys, and then sort according to the ascending order of the first element. So to be honest, I think this is quite hard to come up with this idea to show this proof, but this algorithm actually works. I just tested a lot of cases. It works. Yeah. Otherwise, I think it's time up. So we can. Is there any office hour or other like get-together meeting so we can talk about it if you are interested into more involved examples and projects with advanced combinatorics. All right, I think time up. See you around. Bye-bye.